Welcome back to Introduction to Machine Learning. I'm Ludwig Botmann, and in this video we will have a closer look at some losses that we can use especially for regression. Why do we care at all? So perhaps we feel that the L2 loss, the L1 loss are not good enough for our wishes here, so we want to handle errors in a custom fashion. For example, we perhaps come from a statistical perspective and we have some different error distributions in mind than just a Gaussian distribution, and would like to see what loss functions do correspond to these other error distributions. Another angle is that, as we already have seen, the L2 loss especially is not very robust, but we would like robustness, so against outliers. And perhaps we just have different predictive tasks, because if you think about it, if we use the L2 loss, what we are basically modeling is the conditional expectation of y given x. And perhaps that's not what we try to model, because perhaps we are more interested in quantiles of the target given the features. And there are error distributions for that, and there are also loss functions for that. So what you see here is a plot of the different loss functions that we will cover here. Yeah, let's go through them one by one. The first loss is the Huber loss. The formula seems perhaps, I'm not sure, perhaps it's intuitive, perhaps not. You can decide on your own. But the first part is some L2 part. So we have a quadratic error here. If the residual or the absolute residual is in some area between minus epsilon and plus epsilon. So if we go here at this epsilon equals 2 function, then here in between it's a parabola, and then what happens with this term is that this parabola is extended linearly. So the derivative coming from the right and from the left at these 2 points is equal, so that the derivative is continuous. So what I think the intuition should be about is more like, okay, then here we have the absolute value of the residual and all these other things, so the scaling with epsilon and here subtracting some things just to make the derivative continuous, right? So it's a piecewise combination of L1 and L2 to get the best of both. So L2 is smoother than L1 because it's continuous differentiable, but L1 is more robust than L2, as we have seen. And well, perhaps we get the best of both worlds. So it's convex, it's once differentiable, continuous differentiable. So that's good in terms of these properties, right? The bad news is that we have no closed form solution, even for constant or linear models. So the optimization is a little bit harder, but well, we can do this with some numerical procedure. As it's convex and differentiable, there are a lot of methods that could cover the Huber loss. The solution in the end behaves like this trimmed mean, so a mean of 2 quantiles. Perhaps that helps for intuition as well a little bit. And here on the left-hand side, you have a depiction of what happens here. So for smaller residuals like that one here, we square it. And for larger residuals like that one, we just take the absolute value of exactly that residual. Okay, the next loss is the Log-Cosh loss. So that is the logarithm of the cosinus hyperbolicus of the absolute residual. Cos h is this formula here, and this is also a combination of L2 and L1 loss, so very similar to Huber, but it has a nice property that it's even twice differentiable. Huber loss is only once continuously differentiable, this one here is twice continuously differentiable, but it's also parabola here and then linear function there, and you will see, or I will show you here, how this perhaps strange formula is motivated. So the essential idea is as follows. You take the absolute loss, so the L1 loss, and then you take the derivative of this L1 loss with respect to the residual. Okay, so either you are on the right hand side or on the left hand side from 0, then the derivative is just 1 or minus 1. So it's the signum, the sine function, right? So just the sine of the residual. Okay, so we go this way through these 4 plots. Yeah. So next, we want to approximate this non-continuous function, and one thing that we could use is the tanh function, so tangent hyperbolicus, which is the smooth approximation of the sine function. And then we take the integral of this, go up here, and this is, as you can look up somewhere the log of the cos h function. Okay? So what we have achieved in the end, as already said, is some continuous or some smooth approximation of this L1 loss here. Later we will see pinball losses that are useful for estimating quantiles, and we can use the same trick to get differential pinball losses later. Okay, this is also a little bit foreshadowing somehow to the maximum likelihood estimation versus empirical risk minimization discussion that we will have, because there is also a Cosh distribution. So that means there is some function here, 1 divided by pi, which can be interpreted as a density function, and we call the distribution then Cosh distribution. So this density function is always positive, it integrates up to 1, so it's definitely a probability density function, and it's a location scale type. So theta is the location parameter, which then in the end will also be the expected value, and sigma is the scale parameter, which is not the variance, also not the square root of the variance, but the variance is this thing here, but it covers the scale of this distribution. So if we compare the Cosh density with the Gaussian density, then we see that, well, it's similar, but the Cosh distribution has heavy tails, so there's more probability mass in the tails here and a little bit less here. So the Gaussian distribution has higher values here in the middle, or more probability mass. Okay, and now to the connection between maximum likelihood and empirical risk minimization, because if we use this density now, let's just set sigma to 1 for a moment, and then we want to do maximum likelihood estimation, so then we have to come up with the argmax of the product of all these density functions or likelihoods. But this is nothing else than the argmin of the sum of the logarithm of these cosinus hyperbolicus things, and that's exactly the loss function, the Log-Cosh loss function, right? So yeah, if you don't believe that that's the same thing, then prove it, because yeah, it is the same thing. Okay, next up is the Cauchy loss. I don't really want to speak too much about this formula here. You can read it or not, that's on you. But let's rather have a look at the plot here. What you hopefully see is that this function is not convex, right? So it's convex somewhere here, but then if we go to higher positive or negative values, then this thing turns around and is not convex anymore. So the good thing still is that it is relatively robust towards outliers, even more than Huber and Log-Cosh loss. It is differentiable, which is good for some numerical optimization techniques, but not convex. So yeah, the optimization gets a little bit harder there. Here we have one example of telephone data. Well, it doesn't really matter what the data is about. We have one feature X, which is here the year, and one target Y, which is the calls in millions. The point is more that apparently these are the, well, let's say the normal data points, and we have here some data points that are outliers. So we could discuss if we really would like to call them outliers, if it's that many. Perhaps it's also a valid part of the data turning process that we would like to model, but let's for now just say these values here are outliers. What we then see is that the ordinary least squares estimator, so the model trained using the L2 loss, picks up quite heavily on these outliers, but the other losses don't do that much, and the best one here should be the Cauchy loss, or not sure if it's the best one, but it's the one which is least robust, so the most robust loss, so it is least affected by these outliers, right? So it's the line at the very bottom here, which shows us that Cauchy loss is even more robust than Huber loss. We have two more losses. The first one is the Epsilon-Intensive loss. It's an L1 loss here and there. So if we are outside this middle field here, so if the margin gets, or if the residuals get larger, then it's an L1 loss. But if we are in that area around zero, then we say, okay, we don't really care if we have some errors here. It's not worse to have an error of minus 0.5 or plus 0.5 than having an error of 0. We don't really care in this area. So in this blue area, we say everything is okay. So if it's in that margin, that's okay. If it's outside the margin, then it should be penalized somehow, but only at some point. We can use this for support vector machine regression. It's convex, not differentiable, as you see, but we'll not treat this any deeper for the moment. Another loss which is used more, I would say, is the quantile loss, also called pinball loss. Pinball, because if you look at this thing here and the ball comes in here, then it goes away there, like in a pinball machine. And it's called quantile loss because this is the thing that you would have to use if you are interested in estimating conditional quantiles of y given x. So as I said before, with the L2 loss, you're estimating the conditional expectation of y given x. With L1, you're estimating the conditional median of y given x. And with this quantile loss, you can estimate any conditional quantile of y given x. I think this is best seen at an example again. So here we have one feature x, one target y, and the basic model is a linear model. But the important thing here is that the variance depends on x and not so much the mean of the error is 0. We have some trend in y given x through this additive term here, but the most important thing is that the variance goes up if we go further to the right hand side, so values spread more here than they do here on the left hand side. And if we just use a linear model, OLS or L1 score, then we can estimate this thing here, perhaps quite well if the sample size is large enough. But we don't really see this property of heteroscedasticity, right? So if we use the pinball loss or quantile loss, for example, for alpha is 0.95, then we can estimate this conditional quantile here, which is, for example, used in growth curves, where it is evident that some subgroups are either very well growing or due to, several causal perhaps effects even not growing that well. I won't go into the details here, but it is definitely used in statistics. And that's it for the quantile loss.